Welcome to today's presentation on hydrology and hydraulic design for corrugated plastic pipe. Thanks for joining us for this presentation, and we hope you will get a lot out of it. Last year we released, at PPI, we released our drainage handbook. Hopefully you've had a chance to download content from that. And as part of that release, we're working through various chapters of that content. And today we will be talking through the hydrology and hydraulic design, chapters 5 and 6. Before I introduce our featured speaker today, let me go over a few operational items with you. First of all, this is a go-to-meeting, this is a go-to-webinar format. And so in that format, you are muted. All our participants are muted. If you would like to communicate to me or the speaker, you can use the questions box or the chat box. I'll be monitoring that throughout. As you maybe heard as we started, this is a recorded webinar. We are recording it, and that recording will be made available to folks from our website at a later date. We will try to keep the presentation moving today. We will use poll questions at various points, looking for your interaction. So if you haven't located already in the GoToWebinar control panel, you should see a poll section where you will have the opportunity to respond to polls there. So with that being said, I'm going to start today with our first poll question. And that has to do with what chapters you have downloaded. So you see the options available to you, and hopefully you've had a chance to, anyway, this will give you an opportunity to get familiar with using the poll, and gives us an opportunity to see who's downloaded what. And if you haven't already, this will give you a good reminder that we would like to see you download those chapters for your use following today's presentation. So they're available free for download on our website. All you have to do is provide a valid email address, and you have access to download that content. All right, so I will close this poll. So it looks like we're at about a 60-40 split between those who have got both of them and those who've got neither, and the hydraulics, a couple of people there. So anyway, thank you, and we hope that those who haven't yet downloaded will take the opportunity to do so in the future. So today's feature speaker is Dr. Kevin White from E.L. Robinson Associates. Kevin is the office manager and water resources group manager for E.L. Robinson in Columbus, Ohio. He holds a PhD in civil engineering and has nearly 30 years experience in hydraulics, hydrology, and water management, primarily focused on highway hydraulics. Kevin is also an ASCE fellow and emeritus member of the Transportation Research Board. So please give your undivided attention to Dr. Kevin White.
Thanks, Dan. Dan, do I keep my microphone or my camera on while I'm going through a presentation?
Yep.
Okay.
Yep, that'll work.
All right. So we'll get started. Quickly, what Dan just talked about was for me, but anyway, really quickly on the presentation, who's clicking stuff? Let's get going again.
All right.
We'll just, all right. So quickly about E.L. Robinson, we're in 6 states and generally what I would call the ACC, along with Ohio. We're 100% employee-owned company, and we have about 200 staff throughout those different states. So just a quick plug for E.L. Robinson. Quick overview of what we're going to do today and a rough idea of what the timeline is going to be. Introduction, the first 5 minutes, we've gone through most of that. Hydrology, we'll spend about 30 minutes talking about hydrology, talk about runoff estimations, then we'll do some questions and answers. We'll have a short break, maybe 5 minutes, just for people to kind of stretch a little bit, and then we'll jump into the hydraulics, which is closer to 50 minutes. talk about culverts, storm sewers, detention systems, and then we'll have another opportunity for questions and answers. So with that, we'll dive into it and we'll start talking about hydrology. So when we talk about hydrology, we're really talking about what is the rate of rainfall and what's the spatial distribution of that rainfall. And from those two, we try and target our runoff estimation. And at the end of the day, for most of our needs, runoff estimation is really what we're looking for from hydrology, much more than the actual spatial or rate distributions of the actual rainfall. So for the rest of it, we're going to call it runoff estimation instead of hydrology, because that's essentially what we're doing. We're looking at runoff estimation. So the next poll question, which comes very quickly, is what is the most accurate estimation methodology of the four selected? NRCS TR55, the analysis of gauge data, US regression equations, or the rational method. And this will just open us up to a little bit of conversation real quick before we jump into this. So we'll give you a couple of minutes to put down an answer and we'll see what we get.
All right, get your last votes in and I'll close it and show you the results.
Okay, Dan, I can't see them, so you'll have to tell me.
Oh, okay. I thought you could. So TR55 received 25% of the vote. Analyzing gauge data received 23%, so about an even split there. USGS regional regression equations received 13%, and the leader was the rational method with 38%.
So we all need to go through this presentation because analysis of gauge data is by far number one, not even close. And then second would be the USGS regression equations. And then at that point, it gets a little bit fuzzy because when we start talking about NRCS and the rational method, we don't even know how accurate they are. At least the other two, we can put a bound on it. So we can put an upper bound and a lower bound on numbers 2 and 3 and actually get an idea of what our 95th confidence interval is, or a 90% confidence interval, whatever interval you want to go with. But when we start talking about NRCS, TR55, and rational, we don't even know how good they are. And in fact, depending on where we are and what the basin looks like, those two methods, the accuracy of them changes, and it changes greatly. So when you have a very good state with a lot of gauge data, and Ohio is one of them. Ohio has an incredibly good network of stream gauge data. You can get extremely accurate understanding of what your runoff is at any particular location, to the point where you might have a confidence interval of less than 20%, which is really, really good, which is saying that you're 95% confident that your answer is plus or minus 20% of what you calculated. That's extremely, extremely good. USGS regional is just taking all of those gauges and regressing them. And so you get a little bit more error introduced because it's got a much larger temporal variation. But like I said, the TR55 and the rational are actually two of the worst methods that we have. And I say worst with a little bit of a grain of salt because they're still very, very useful in what we do. And because of their ease of use, they have an extremely high utility. Right, so that's what we said. And the reason that the gauge data is so good is because it's an actual historic data set at the site in question. So you've got an extremely powerful tool. Okay, so what are we trying to do here? We're trying to find out what's a peak volumetric rate of runoff or a temporal distribution of runoff at a individual point of solution. There's significant natural variability in these systems. So different methods, when we talk about those 4 different methods, or probably the 4 most utilized methods, we can have extremely different results, as much as 50 to 100% different results. The other thing I would say, and this is really, really important, is that hydrology is as much an art as a science. And so really what you have to think about is what is the level of effort involved in any given runoff model that you choose to use, and is the extra accuracy gained commensurate with the importance of the system. So what I'm getting at there is, if you have a culvert that's in the middle of nowhere, and if it floods up behind it, no one gets damaged, nothing gets hurt, do you really need to go through the effort of going through gauge data and things like that? You probably don't. A simple rational equation is usually good enough. So understand the importance of the system when you're determining what is the right runoff method. So the first thing we look at is gauge data as a method. The three most popular distributions are the Gumbel distribution, the log normal distribution, and the log Pearson type 3 distribution. And so what you see in the charts is the difference between a log normal and a log Pearson. And this is at a river that I actually worked on. So what you see is when you use a log normal, say take it the 100-year return, which is at the bottom, you get 79,000 CFS. When you do a log Pearson type 3, you get 82,000 CFS. Well, those numbers are less than 5% away from each other. So, but the effort involved in doing a log normal versus doing a log Pearson is fairly substantial. You take easily an extra couple of hours, if not longer, to do a log Pearson versus doing a log normal. But then you see the difference in the estimation, and you say, is that 5% worth the extra time? And so that's kind of what I was getting at. Then if we plot it, which is right above, you see the plot where the solid line is the log Pearson estimation, and all of the cyan dots are the actual runoff values that were taken from the gauge station. So you can see in the lower events, the higher exceedance probability events, our results are much better. But it starts only getting out to the extreme events when we start losing our predictive capacities. And that is really more a function of the number of years of record that you have. And in this case, you can see that our longest gauge data point is probably somewhere in the 60 to 70 year range. And so that's kind of, that's a reasonable gauge data set. And even there, we get some fairly high error in our predictions. But anyways, this is the best we have, honestly. We can then, so next we'll look at some important factors that we need to consider when we actually get into trying to predict our runoff. And one of the most important ideas that we have to get across is this idea of an intensity, duration, frequency, and what that means. The intensity is the rate of rainfall, the duration is the time to peak, and the frequency is the probability of a runoff event in any given year. So in the old days, we would say a 10-year storm, 50-year storm, 100-year storm, and 10-year storms a 10% exceedance, 50 years a 2% exceedance. Currently, there's a trend to move away from saying something is a 10-year storm or a 50-year storm, and instead we say it's a 10% exceedance or a 2% exceedance. And the reason that they do that is because it gives the public a sense of security that doesn't exist. So I had a 10-year storm this year. That means I won't see another 10-year storm for 9 more years. And that's kind of the thought. It only happens every 10 years. And that's just not true. And so that gave really a false understanding of what this meant. So there's a real trend away from that right now. And what the chart looks like is a normal IDF curve chart. So you have your duration along the x-axis, your intensity along the y-axis, and each one of those curves is for a different recurrence interval. Previously, we mentioned the time of concentration in the last slide, so we'll talk about it more here, and we'll say what is the time of concentration or the duration of the rainfall. Typically, we break it out into 3 different components. Overland flow, which is sheet flow, which is basically from your top of your watershed for about 100 to 300 feet, depending on who you ask. That's another interesting thing that I'll bring up is all of when I talk about ranges, it's because there's uncertainty in the amongst the experts, and depending on what agency you talk to, you'll get different answers. And so for overland flow, it can vary anywhere from 100 to 300 feet. So the way that you estimate it is either by the Kirpich equation or the kinematic wave equation. If you look at the kinematic wave, what you see is you see that the overland flow time is a function of the intensity, which is that small I in the denominator. So what happens is what you're really trying to figure out here is the intensity. If you go back one slide, look, so what we're trying to target here is the intensity from the duration and the frequency. So you'll notice here, to get the intensity, we have to know the time, but so this is circular and this is an iterative equation, whereas the Kirpich is not. Kirpich is just based on the length of the basin and the slope of the basin, and that's it. So from a calculation standpoint, I prefer Kirpich just because it's easier. Shallow concentrated flow is as water gets in the rills and small gullies, and then finally your concentrated flow, and for that you just use Manning's equation. Now there's some really nice charts, and the chart at the right is a chart that tells you what's your average velocity for shallow concentrated flow, and based on the water slope, and then from that you know your distance of your shallow concentrated flow, so you can get your time of concentrated flow. And then when you actually get into or shallow concentrated flow. Then when you actually get into concentrated flow, that's like a river or a stream or a larger gully. And for that, you just use Manning's equation. You add up those 3 times, and that's how you get your time of concentration. All of that leads us to the rational method. Because what we really need out of the rational method is, right, CIA. Oh, I forgot A down there, I apologize. But Q equals CIA. So Q is your peak rate of runoff, C is your runoff coefficient, I is your rainfall intensity, and A is your drainage area in acres. Now, what's interesting about this equation is that if you go through the unit conversion of it, there actually is a slight unit conversion that needs to take place, but it's so small that we typically ignore it. It's about 1%. It's actually 0.0083. So for all practical purposes, we just say it's Q equals CIA, where C is your runoff coefficient, I is your rainfall intensity, which we just talked about. So next we'll talk about our runoff coefficient. And what is our runoff coefficient? It's basically an indicator of how much rainfall is converted into runoff. And it's a single value. For larger drainage areas, you have to start using composites, where if you have part of your drainage area is paved and part of it's rural, you start using a weighted average of the area for the different runoff coefficients. And the tabular values are available all over the place. There's tons of locations to get these C values. When we talk about the rational method, it's important to talk about what are the assumptions of the rational method. And the 3 fundamental assumptions are, number 1, that the peak flow occurs at the time of concentration. The way that happens is by us using that intensity. We figure out the time of concentration when the entire drainage area is contributing. And that happens at the longest flow path in the drainage basin. So that's one of the main contributing factors to error that occurs in rational method, is the fact that you have what's called a basin lag. And that's the difference between your time of concentration and your location of peak volume of runoff. We also assume a uniform rainfall over the entire watershed, which for larger watersheds, right, is really not reasonable to assume. And the last thing we assume that the rainfall frequency is equal to the runoff frequency, which means if you're getting a 5-year rainfall, you're getting a 5-year runoff. The larger the watershed becomes, the more these 3 assumptions become non-valid. So what we tend to do is we tend to limit our watersheds for rational method to smaller watersheds, perhaps 200 to 300 acres, and some would say even less. finally, we'll talk about NRCS TR55. This equation takes a slightly different form from the rational method. And what we end up here is our peak discharge is equal to our unit peak discharge times the drainage area times what's called the direct runoff. Now, keep in mind that this is the variable is Q. This is not the same Q as what we use in the rational method. So I'll just keep that in mind. The other interesting thing is that this Q sub U, the unit peak discharge, is in cubic feet per square mile per inch. So when we talk about TR55, first thing we have to talk about is our soil groups, and they're called hydrologic soil groups. And it's a classification system based on the infiltration potential of a soil. And they're A through D, where A has the highest infiltration potential, sands, things like that, and D is the worst, such as clays. Nifty tool out on the web is called the Web Soil Survey. And from that Web Soil Survey, you can, if you wanted to, you can actually import a shapefile into the Web Soil Survey, and then so for the drainage area that you have, and it will actually come through and it will give you the constituency of all the different soil groups and what different soil class they are for that particular basin. So it's a neat tool, and what it tells you is so if we look at this particular drainage area, this is predominantly C's and D's, which, you know, this is an Ohio area that I pulled, which if you're in Ohio, it makes perfect sense to you because Ohio is full of C's and D's. So basically it means that you have very, very low potential for infiltration of water into the groundwater table. You just don't get that happening very well. Next thing about runoff estimation in TR55 is looking at a runoff curve number. And this is similar to the C value that we use in the rational method. This is an indicator of the runoff potential, and it's based on those different soil groups. And again, there are tables, you can go onto the web and you can find hundreds and hundreds of these tables built for every possible land type and land use that you possibly want to consider. But what you see here is you see that based on the hydrologic soil group, the A, B, C, and D, we get different runoff curve numbers. And that's an important understanding of what's actually happening, and that depending on the soil group, you have lower or higher potential for runoff. Next concept with TR55, and bear with me here because I know these all seem like independent sort of concepts, but they all kind of tie back together at the end. So we have a concept of the initial abstraction. And basically the initial abstraction is your losses before runoff starts. So capture of water and surface depressions, transpiration, evaporation, all these things that happen before water starts running off. And so what you're trying to figure out is you're trying to figure out how much loss you have before you start getting runoff. There's a number of nomographs for this with TR55, so you can actually calculate these values, so you can actually get the values from a chart, or there's a nifty relationship that someone came up with where your initial abstraction is equal to 0.2 S, where S is your maximum retention after runoff begins, and S is equal to 1,000 times or divided by your runoff curve number minus 1. So if you're looking at it from a spreadsheet standpoint, that equation is certainly much easier than trying to go about it using nomographs. Next thing we talk about is our unit peak discharge in the Q sub U. And the reason that we talked about the initial abstraction, I sub A, was because we need the I sub A value in order to determine what's our unit peak discharge. It's an empirical relationship based on different rainfall distributions. And so what TR55 did was it divided the country into 4 groups. And it said within these 4 groups, the rainfall, what a normal typical storm looks like for any one of these 4 groups. And that's how they grouped it. And so what we end up with different charts for each of those 4 different groups. So in order to look at this particular unit peak discharge, we need a time of concentration, and we need this IA, which is the initial abstraction, and divided by the rainfall P. And so for different values of IA over P, we can go into this chart and find out what our unit peak discharge is based on different times of concentration. The last thing we need is this runoff Q. And this tells us what's the excess depth of rainfall that's available that can be converted to runoff. And that's based on P, your rainfall in inches for the given recurrence interval, and your initial abstractions and your S value. Again, there's charts for this inside of TR55, but somebody developed this nice equation. And if you actually want to do it by an equation, you can use this particular equation. Last thing is our unit hydrograph. And if you've ever dealt with TR55 and done this by hand, there are 50, 60, 70 pages of TR55 that are devoted to these tabular hydrographs. So what this tabular hydrograph does is if you look at on your y-axis, you have your time, and that's your time of concentration. And then across the top, you have your hydrograph time in hours. And so what you see is you see that using this particular area, this distribution, runoff doesn't start until time of 9 hours, and it continues through time of 24 hours. So what we do is we go into this particular chart. If we look at, say, time of 0.0, go across the hydrograph time of 9.9, and we drop down, we have 183. What that's telling me is I take that 183 and I divide, well, I multiply it because that's it's per square mile per inch of runoff. And so I have to convert that number based on the values that I got in my unit discharge and my drainage area. And so that's how I convert these numbers. And from that, I can actually go along the x-axis, picking values, and I can build a hydrograph using that particular method. Okay. And you end up with something that looks like this. You end up with a hydrograph. And when we look at it in terms of TR55, it shows you sort of what is your direct runoff, what does the actual your rising limb, your receding limb, and where your peak is, and what is the overall time of the particular rainfall event. Okay. So at that point, we sort of wrap up runoff. I honestly don't know if we're doing well on time, if we're ahead of time. Oh, we're pretty much spot on. Perfect. So with that, I say, are there any questions? So Dan, has anybody chatted any questions?
Yeah, we've received a few. Some of them have been answered, but so what would be your recommendation, Kevin, if there isn't gauge data, then what would be your recommendation that they go to instead?
It depends on a lot of factors. If it's a stream, and your state has good data, I would always look to the regression equations first. I think the regression equations are highly, highly valuable and probably highly underrated. After that, you start getting into nuances about how big is the drainage area, what is the makeup of the drainage area, and that would lead me to what method I want to use. In general, so think of it in this terms, really, if it's a smaller drainage area, typically the importance of the structure and the likelihood of flooding under those conditions are reduced. And so rational usually is a good bet when you're in smaller drainage areas. As your drainage area gets larger, that's when you start looking at NRCS. The other time you look at NRCS is when you're not looking at it from a steady state. So if you aren't just looking at peak discharges and assuming peak discharge throughout the watershed, and you actually want to understand what's happening over time, rational isn't terribly good at time domain. So in that particular instance, I would look to NRCS. So that's kind of how I would go about it. But I wish I had a better answer, but as I said earlier, there's a certain art to this as much as there is a science.
Great. There was also a question about just confirming then what does a 10-year event mean, for example, on those frequencies? I attempted to answer that in the chat area. Basically, weather events don't have memory, and so it's a probability, and whether it happens today, Mother Nature has no recollection that it happened today. When tomorrow comes, it's still the same probability.
It's a
That's kind of
10%.
how I think of it. But I don't know if you have any other ways of explaining it.
That's it. In any given year, on any given day, that it's basically it's telling you that in this particular calendar year, you have a 10% chance of that event occurring. And that's what it means. Nothing more, nothing less.
Yeah.
And but you can get 4 10-year events in one summer.
Right.
The probability of that is extremely rare, but it can happen. And
Sure.
it's not unusual. And today, so we can talk about climate change and what we can tell you. I'm not going to get into the argument of is it real, is it not real? That's not for me to answer. What I can tell you is that when we look at the statistics of it, the last 20 years, we have had much higher frequency of storm events than in the past. So what I'm getting at is if you look at the statistics of it, we've had large rainfalls in the last 20 years than we've historically had. Whether that's a statistical anomaly, whether that's because of natural man-made climate change, whatever you want to say, you cannot argue with the statistics about it, which is that the intensity and the frequency of floods are increasing.
Right. Well, I think if you wanted to offer a little break here, is that what your plan was?
Yeah, just take a short break, a 5-minute break, because the next part is a heavy lift. So
Yeah. So
everyone,
why don't we make it like 3, just so that we stay on track. If you need to respond to something, check your phone, then do that, and we will begin in 3 minutes again.
thanks, Dan.
And there are a few questions. I don't know if you want to look through those, if there's anything you want to respond to. One question that we didn't talk about, Kevin, was access to the slides themselves. My response is that we will be recording this, or we are recording it, and that will be available from our website. But actually, slide content, that's your own stuff. So I guess I need to defer to you as to whether you would share your specific slide content with any attendees.
I'm not opposed to it. I don't have a problem. It's there's nothing here that's special. I would say it
Right.
that way. This is all pretty
Right.
strict.
I mean, it's in our handbook. A lot of the content is in our handbook. A lot of the stuff that you're pulling up is public information and such. So just trying to bring it all together in one place.
Yep, exactly.
Okay, well, we've given our 3 minutes, so I was hoping we can get started again. So Kevin, when you are ready, we will get started.
Great. Okay, so next we're going to dive into hydraulics. A little bit more in depth here in terms of the content. So we have a lot more time segregated to set apart for this. So we'll get started. Some of the fundamental concepts that are important whenever we talk about open channel flow, hydraulics, whatever. That's the continuity equation, Q equals AV. So runoff is equal to area times the velocity. It's an absolute fundamental equation of hydraulics that if you don't know it, you ought to know it. The second is Manning's equation, which everybody I hope has also heard of. A couple of fundamental concepts when we talk about open channel flow, steady flow, uniform flow, and gradually varied flow. These are typically what we assume when we're talking about open channel flow. And steady flow means that there's no change with time. So it means that there's no change in runoff. And this is what I talked about before, where we talk about a peak discharge and a steady state. And so it's actually steady flow. Uniform flow means that there's no change with distance. And that means that your cross section that the water is flowing through remains the same no matter how much distance you travel. And what's gradually varied? Well, gradually varied means that we can change those things. We can change the time, we can have a change with time, we can have a change with distance, but they're happening so slowly that we make the assumption that the flow is steady and uniform. And that is generally what we do when we talk about open channel flow. Now, river flow, that's different. River flow, we often will not make the same assumption. So the fundamental equation of open channel flow, as I talked about, is Manning's equation, where we're talking about our velocity is equal to 1.486 over the Manning's number times the R squared hydraulic radius, R to the 2/3, R is the hydraulic radius, which is the area over the wetted perimeter, times the slope to the half. We can substitute velocity for, if we go back to our continuity equation, Q equals AV, we can make that substitution and we can instead solve for Q, our discharge. And so now we see our area pop up into the right-hand side of the equation. Essentially, Manning's equation is an implementation of the Chezy equation. And so Chezy got kind of short-changed here because this was the fundamental equation of open channel flow. And then Manning kind of robbed him of his thunder, and everybody knows it as Manning's equation, even though it's really an implementation of Chezy's equation. But it requires empirically derived roughness coefficients, which is our end value. And we have lots and lots of tables that tell us what our Manning's number are. A little brief look in the table that I provided to show some of the pipe materials. Keep in mind that the number that you get is it's a design value, and because the Manning's number changes with the depth of flow, it changes if there's joint gaps, the spacing of the joint gaps. It depends on the shape of corrugations. If there's corrugations, there's so many factors that are involved in a Manning's number that we assign one number to a design. And that's because we're designing it. We only want to design it once. And so, but keep in mind that number changes. Not only that, but the number changes with time. And so as the pipe ages, the Manning's number changes. So with that, I'm going to let Dan talk a little bit about PPI and their take on the Manning's equation and coefficients.
Right. So you saw what Kevin showed had a range basically for every pipe material type. There's ranges. And so as an industry, it's important for us to have a consistent recommendation. And our industry recommendation within the corrugated plastic pipe industry, whether it's HDPE or polypropylene with a smooth interior, is to use a Manning's coefficient of 0.012. This has been supported over the decades, basically, of research that's been conducted both at Utah State Water Research Lab as well as Colorado State and their water center there, and it's been supported over a variety of diameters and again over time. So that's where we came kind of come to rest as an industry recommendation. As far as our test results, though, some of those test results came in below 0.012. It's not that we took the minimum number that was ever shown and that's what we used. There's a variety of numbers across the course of a series of tests that are run. Some of them are 0.010, which is great, but it's not something that we recommend for design. And that's kind of Kevin's point. You got to have a number that you're going to design with. And by going to 0.012, our intent is to take in figure that we have accounted for some of those things in the field, such as slight joint misalignment, or there might be some sediment in it. So if you go too low, if you try to scrape the bottom on that number, you're just going to hurt yourself later with design. And so we feel like there's some conservative built into 0.012. Typically, we're not looking to downsize compared to concrete pipe. Most often, I know concrete pipe uses a Manning's coefficient of 0.013. That thousandths of a different than the Manning coefficient shouldn't make a diameter change difference. And so really, in most cases, compared to closed concrete pipe systems, we're looking at comparable hydraulics. Now, if you're comparing it to corrugated metal pipe or something, then that obviously could result in reducing a diameter. But in most cases, in closed systems, we're not looking to do that. So one of the other questions that comes up is that sometimes if you look at installed corrugated plastic pipe, you can make out a little bit of indulation within the liner as it moves from corrugation to corrugation. And there was research conducted on that phenomena specifically and found that having a little liner indulation really does not change the hydraulics at all, even when that was intentionally induced. It did not impact hydraulic performance. So that question comes up. But I wanted to then move to the next poll question. Sorry. And I'll just launch the poll question. That's so I talked about smooth interior, but what about single wall corrugated HDPE pipe? Single wall is still used quite a bit, definitely in land drainage applications, but you could find yourself in a situation where you actually want higher Manning's coefficients. Maybe it's a steep slope or something like that where you're actually trying to slow the water down. So what Manning's coefficient, how do you determine Manning's coefficient for single wall pipe? So if you would get your votes in, I'll give it a couple more seconds and we'll talk about this briefly and then turn it back over to Kevin. All right, last one's in. All right, very good, thank you. All right, I'm going to share the results. So the results come in, the highest vote getter is the correct answer. It does vary by diameter, and it does kind of vary between the 0.016 range and the 0.024 range. And it really has to do with the larger the diameter, and some of our members make 24-inch diameter single wall pipe. That's gonna be closer to the 0.024, just because you think as the diameter gets bigger, the pitch of that corrugation gets bigger also, versus small diameter. Like if you're talking 3 or 4 inch diameter, then it's going to be less of a pitch, less of a drop, and that water can quickly move through it. So on those diameters, it's going to be on the lower end, but it does vary by diameter. I would check with your manufacturer for recommendations, but it typically does vary between 0.016 and 0.024. So a little bit of a trick question, but varies by diameter is the correct answer.
Okay, so we'll take over. And now why we talked about open channel was because the next thing we're talking about is storm sewers, and that's an implementation of open channel flow. And what we're looking at is we're looking at generally what's the depth of flow in the pipe and what's the velocity of flow in the pipe and how we get to that is through Manning's equation. The other thing we always have to be concerned with is our hydraulic grade line. And the next slide, I'll talk more about the hydraulic grade line. But hydraulic grade line talks about the depth and velocity, but it also has to include all of our system losses. So we actually have an understanding of what is the depth of flow of water within the system. And especially when we're in a closed storm sewer over long distances, where we can actually get into slight pressure flow. And so that at any given junction, the water will actually be higher than the pipe diameter. When we talk about hydraulic grade line, we talk about conservation of energy, and more importantly, Bernoulli equation. If you all can remember back to college when you talked about Bernoulli, what we do is we basically start at the downstream end and work our way upstream. And what we do is we take into account the datum change, so the change in elevation, friction losses, and minor losses. And I'll talk more in specific about those. But what you can see is important on the graph, you can see the water surface, which is the hydraulic grade line, and you see the energy grade line. And the energy grade and the hydraulic grade are separated by what's called the head, the velocity head. So the V square over 2G, and that's your velocity head. And so this gives you an understanding of the energy in the system. And so that potential, that potential energy matters, and it can matter drastically, as I'll show you. So friction losses, first thing we talk about, that is a loss in the barrel between the pipe and the water itself. And you calculate it using the friction slope, which is just a manipulation of Manning's equation. So we do some manipulating of Manning's equation. We solve for the slope instead of solving for the discharge. And from that, we can actually calculate what is the friction slope. So when this becomes important is when your friction slope is steeper than the slope of the pipe barrel. So you can imagine if we start at the downstream end, and if we're going upstream, but we're going upstream at a slope that's steeper than the pipe, eventually we're going to go above the top of the pipe. And that's when the hydraulic grade line becomes a concern. Other thing are minor losses. They're always in some permutation of a K value times V squared over 2G, where V is your velocity and G is your gravity. K is your coefficient for your minor losses. And there's lots of different losses to consider: bends, contractions, expansions, junctions. And what you see in the chart on the right is for a bend. Now, the reason I threw this in here is so you can see that for most cases in a storm sewer system, we're talking about radiuses that are very, very large in comparison to the diameter of the pipe. So we end up on that chart really, really far to the right-hand side, and our losses become very, very minor. And so bends in general contribute very, very little loss to the system. Where we get our most loss is actually in junctions. Expansions and contractions are some, but junctions are where we get the most of our losses. And what you see here is you see what happens when you haven't considered everything quite properly. And as you can see, there's a storage vehicle, the white truck on the left-hand side of the picture, and you can see that the water coming out of this particular manhole is nearly to the top of that truck. And this was a picture taken at a site where actually what ended up happening at this particular site was the estimation of the hydrology was not correct. We coupled that with extremely high velocities, and we ended up with a situation where we had a very large loss. I'm going to go back to our equation, and we see that, again, our loss equation is a function of V squared over 2G. So as V increases, our junction loss increases, and they increase in a power function. So if we end up with really, really large velocities inside of a sewer system, you can end up with incredible results at your junctions that you absolutely have to be aware of. So The other thing that's important about velocity when we look at our velocities, we have to look at that our high velocities are indicative of generally supercritical flow. And at the end of the storm sewer, when we finally flatten out and we end up into the stream or wherever we end up with, we can make a transition from supercritical flow to subcritical flow. And whenever we do that, we get a hydraulic jump. And the issue with that is if we get a hydraulic jump, we can actually end up with a negative pressure in the pipe, and you can actually pull the pipe down from that negative pressure. So typically we would vent it, or we would do something to try and say where we want that hydraulic jump to occur. And that way we can avoid damaging the pipe. Next, we'll move on to culverts. We have to consider the location, which is the length and the slope, the size and the shape. The shape, rounds are by far the most common, and the reason is because they're very hydraulically and structurally efficient. So and honestly, they're actually cheaper to produce. So they're cheaper and they're hydraulic and structurally efficient. But there's numerous other shapes, as many shapes as you can think of. Somebody is making a culvert in that shape. When we talk about culverts, we always have to go back to HDS 5, Hydraulic Design Series 5 by Federal Highway. That was originally HDS 5 by the Bureau. It was actually BPR 5 back in the day, back when the first permutation came out back in the 50s. That was by the Bureau of Public Roads, which was a precursor to FHWA. And they had their BPR 5. And that was the beginnings of culvert hydraulics. And that's where we got this concept of inlet control and outlet control. So when we talk about inlet control, what we're saying is that the inlet configuration controls the hydraulic performance. The easiest way I can explain this is if you think about the drain in your sink, and when you take the cork out of it or the stopper out of it, and there's all the water can't get down into the barrel quickly enough, that the pipe down below isn't running full, and that pipe's only running half full. It's because the inlet is shaped in such a way that water can't get into it quickly enough to completely overwhelm the pipe below it. That's about the easiest way I can say what inlet control is. Inlet, so basically the inlet section controls the design. Outlet control is when everything matters. And this is more of becomes a permutation again of Bernoulli. And you actually have to look at our system losses. And so we have to consider the inlet configuration because that gives us our inlet loss, the length and the slope, which gives us our overall friction slope and our friction loss, which is coupled with the roughness, which also talks about our friction loss. And then we got to talk about our outlet configuration, which is our outlet loss. And finally, we have to think about the downstream boundary condition, which is the tailwater at the outlet of the pipe, because that's going to be our starting water surface when we go through this calculation, back thinking about Bernoulli. In general, I always talk in general terms. I hate to get too much out of this, but inlet control is on steeper slopes and smooth barrels. And outlet control is on gentle slopes, rough barrels, or long lengths of pipe. And so that's when those two generally, and there's no number. Every time I give a presentation, somebody says, well, what are the numbers? When does it switch? I can't tell you that because it depends on a lot of different factors involved in the hydraulics. But in general, the flatter slopes end up in outlet control. As I talked about HDS 5, they give you a bunch of nice nomographs for calculating inlet control and outlet control. And Dan, I apologize, but these are for concrete pipe. But they don't have they didn't have polyethylene pipe in 1964 when this chart was developed, and they've never been updated for polyethylene as far as I know, because it doesn't make a difference. This is for a smooth barrel and for a particular type of entrance. So the same nomograph applies. But we also have free software, and everybody loves free software. And Federal Highway put out a program called HY8, which is free for download. If you go to Federal Highway and just if you do a search and type in Federal Highway HY8, it'll take you to a web page where you can download this particular piece of software. And this is an absolute exact permutation of HDS5 with a couple of small variations. I don't want to make you see that it's exact, because there's a under inlet control. There is a change depending on the headwater where the inlet will switch from acting like a weir to acting like an orifice. Now in HDS, they don't really try and differentiate. They just take the higher number. Whereas the software fitted a polynomial curve between the weir curve and the orifice curve. And so that way it becomes a smooth function. And so in a computer sense, it's a nice way to get one curve to kind of take care of inlet control in general. So that's just a very small difference of what you get. But that's really about the only difference. Okay. Last topic is stormwater management. And when we talk about stormwater management, we really are talking about water quality and water quantity treatment, the two big goals of stormwater management. So when we talk about water quality, we're talking about measures to reduce pollutants. And it's really, really easy to get rid of particulates such as granular soils and other solids. That's very simple. And there's lots of ways we can do it. But when we start getting into fine grained soils, things like clays, it starts getting more difficult, to the point where you could take a sample of water and put a really fine clay into it, an A27, for example. And you could let that sit on a shelf for weeks and it'll still be turbid, because the ability to get those fine grained soils out of solution, not out of solution, but out of suspension, is very difficult. But then when we talk about metals, and we talk about metals that are actually in solution, it's nearly impossible. It has to undergo a chemical process to get these metals out of solution, and understand the difference between being in solution and just being in suspension. And suspension is just floating around still as a particle. But when it goes into solution, it's actually created a chemical bond with something else inside of the water solution. And so getting it out of that chemical bonding is extremely, extremely difficult. So when we talk about water quality, you always have to be cognizant of what's the goal of the water quality. Okay. And really, from a water quality, that's probably as deep as I'm going to get today, which leads us to our next poll question. Before we get into our detention calculations, I just wanted to know, have you ever performed detention calculations by hand? And I'm interested to see. Okay, Dan, let me know what we got here. I think you're muted.
Yeah, we've got 2/3 yes, 1/3 no. Oh, sorry, the other way around. 2/3 no, 1/3 yes.
I was going to be shocked. I was literally I was almost ready to fall off my chair.
If it had been the other way around. Sorry, I about sent you to the floor there. So we had about 1/3 yes, about 2/3 no.
And that's actually, wow, I'm actually impressed, because that's a large number, a third that have done it by hand. So that's what we're going to talk about today. We're going to talk about what are we trying to accomplish, and what you're going to find out is it's really not that hard. The only real difference, I would say, and some of the guys, girls who are on the webinar who have done it by hand, I think the only difference really between doing it by hand and doing it by computer is how small of a time slice you can do. So if you're doing it by hand, you're using sort of 15-minute time slices. Whereas if you're doing it on a computer, it's nothing to say you're going to do 1 minute. But so, you know, there's some, besides that, I'm not convinced that there's much of a difference between how the software does it and how you do it by hand. So, all right, we'll keep moving. And then with this, I'll let Dan kind of talk about the detention systems and why the HDPE and PPP are good for detention.
Yeah, this is one of our areas where we feel like corrugated plastic pipe does quite well, whether HDPE or polypropylene, both have great characteristics. One is obviously HDPE and polypropylene are very inert to things that you would normally find in runoff. And that includes the road salts. You know, typically if you're in a northern climate where they have snow and ice and things, road salts are applied. And if those find their way into a detention system, there's a good chance those are going to sit there for days, weeks, maybe even months until a good spring rain kind of flushes the whole thing out. And so road salts can be real hazard to an underground detention systems where you've got a lot of volume or a lot of area and very little velocity moving through it. So anyway, that's one area. Fabricated fittings with plastic pipe have the ability to fabricate fittings, which makes it easy to do size-on-size manifolds or reducing manifolds or bins or other types of reducers that you might want to implement in your layout. I'm having trouble advancing this slide. There it goes. So a lot of manufacturers also supply support for this process with some standard details or assistance in laying out. There's a lot of good helps offered by manufacturers in this step of the process. With plastic pipe, you can also stay solid, as most people think of, or it can be perforated. Plastic pipe can be perforated so that if you want to take advantage of the void space of the stone backfill around it, or perhaps you live in an area where there's sandy soils and it actually infiltrates, so that provides an opportunity to return some of that water back into the groundwater system. So void space in stone, our industry recommends 28% of the clean crushed stone be used as available space for storage if you use a perforated system. Kevin just talked briefly about water quality, but large diameter corrugated plastic pipe can be equipped, fabricated with baffle plates to supply some type of sediment control. And I think for an underground detention system, certainly one where you're using the void space in the stone, you will need some type of water quality device at the front end to centrally collect sediment as a minimum, so that when you have the opportunity to clean out, you can do it without having to clean out every single run. That would be the purpose of a water quality device ahead of a detention system. Again, like I said, you're sending a lot of volume with a slow velocity, which means that over time, suspended solids are going to settle out. So having a central collection point would be ideal. There's minimum cover expectations or requirements for corrugated plastic pipe. Most of it's a foot under traffic, but if you're above 48-inch diameter, you're definitely going to want to see 2 feet of cover there. And we also recommend inspection of systems. And so that means providing some type of access to them is recommended so that these systems can be inspected. That doesn't have to be man access. That could be an inspection port that surfaces so that a camera can be placed into the system, again, to look for sediment or anything that might be building up. That's just a general recommendation that we include.
Okay. So back to what we're trying to accomplish here, which is stormwater management and water quantity. So what we're really trying to do is we're trying to mitigate the increase in peak discharge and the total volume. And what you see in the chart is a post-developed hydrograph and a pre-developed hydrograph. And you can see that both your peak and your volume are substantially higher for a post-developed, where the volume is the area underneath the curve. And so what we're trying to do is we're going to try and mitigate that. So what we do is we have to reduce the outflow discharge as compared to the inflow discharge. And so what you end up doing is you end up in a situation where you actually have to store some water. And the amount that you have to store is what I have here shaded in, I think it's blue. I'm colorblind, guys, so I apologize. But I think that's the blue. And that's what you have to store. And in the old days, we would actually go in and we would draw these curves and we would measure that area roughly. And then that's about how big of a pond we knew we needed. And that's how we would start doing our calculations. We do it by hand and we figure out that volume change. And that's what pond size we thought we needed as a beginning point.
You are correct, Kevin. It is blue.
Oh, perfect. that was a guess. I have to be honest with you. So what are we doing? We're doing stormwater routing, and that's what we do. And it's called the modified poles or the storage indicator method, depending on who you ask. And it's a implementation of the conservation of mass. And the equation looks like below, where our delta S, which is our change in our storage, or our change in time, is equal to our inflow at time 1 plus our inflow at time 2, the average of those, minus the outflow at time 1 plus the outflow at time 2, average. And so if you remember back to your calculus days, what we're doing is we're taking a time slice of that particular curve, remember integration, and we're taking a time slice of that curve, we're averaging it, and we're using that as the inflow and outflow. And from that is how we're actually going to get to the amount of storage that we need for any given time slice. I'm always big on free software, so I'm going to talk about HMS by the Corps of Engineers. This particular software can do routing for you. It does a heck of a lot more in terms of hydrology, but it actually can do stormwater routing. So if you're looking for a free piece of software that can do it, here's one for you. So now what we'll do is we're going to take that initial equation, we're going to start manipulating stuff. And what we're going to do is we're going to manipulate it so that the things that we know are on one side of the equation and things that we don't know are on the other side of the equation. And then what we're going to do is we're going to start building a spreadsheet to kind of figure out how are we going to solve all of this. And that's kind of where we're heading next. So what we need is we need an inflow hydrograph, we need a stage discharge relationship, and we need a stage storage relationship. That's all we need. From those three things, we can determine everything necessary to solve this equation. So what do these mean? Inflow hydrograph, we know what that is, right? We've already talked about the inflow hydrograph. That's just the rain flow runoff. Well, when we start talking about a stage discharge relationship, so what this is this a curve that says for your outflow device, based on how much water you have ponded at the inlet of it, how much water comes through the system. And I couldn't find a really good picture that was what this is a curve of. But what this is a curve of is this is a catch basin. This is a very, very common outflow device. It's a catch basin with a small hole at the bottom of the catch basin and then the top grate. And so what you see in the steep rising limb is you see the hole at the bottom. Then at about a stage of about 6 feet, you see the catch basin grate take over, and you can see it run until you get that curve heading up. And what you see there is that's when the catch basin grate changes operation from a weir to an orifice. And once it goes into orifice, then you get an incredible amount of discharge coming through the top. But what you can see is you can see that in the early stages, you don't get a whole lot of water coming through it until you get into your upper range. And that's exactly what you want to have happen. You want to hold back the lesser events, but let the larger events go through. Stage storage relationship. Well, this is pretty simple. And this is how much storage do you have at any given stage? And you get it from the contours of your pond. So you just calculate and do end area calculations on the pond and you get your stage storage relationship. So now what we do is we build our storage indicator table. And this is just our first step. This is the initial stuff we need in order to be able to do the actual routing. And what we do here is this is a stage table. And what we do is we build a stage table. And so based on any given stage, we can calculate the discharge, right, from our stage discharge curve. At any given stage, we know our storage from our stage storage curve. And we just started to do some math on that. And we'll say, okay, we're going to take O2 over 2, and that's column number 4. We'll then take column number 3, and we'll divide it by the time slice that we're choosing to use. Now keep in mind that that time slice, we have to keep it consistent between our two different tables. We're going to move to another table in 1 second. Whatever the time is you choose in the beginning, you use that same time throughout it. And then finally on column 6 is we do a little bit more math. We have S2 over delta T, which is from column 5, and we have O2 over 2 from column 4, and we add those two together. And that's how we get the S2 over delta T plus O2 over 2. Then we actually go through, and I'm sorry, this still says storage indicator, but this isn't. This is the actual routing table. I apologize. Now what we're going to do is we're going to switch over to time, and we're going to use time as the same time increment that we used in the storage indicator table. That's really, really important. If you don't use the same time, your results won't work. They'll be wrong. You'll get an answer, it just won't be right. So then from this particular table, from our inflow hydrograph at any given time, we know what our inflow is. And we also know what I1 plus I2 over 2 is from our hydroflow, or from our hydrograph. And so we can figure out number 3. If you remember, we have S1 over delta T plus O1 over delta 2 from our previous storage indicator table. And then through some manipulations, we can get our columns 5 and 6. Those are just math. You're just doing simple math. And from that, you can calculate your O2 because all the other different parameters in 6 are known now. So it's just a matter of isolating O2. And from that, you get your outflow. And that's your outflow volume coming from the pond at any given time. And that's how you develop your outflow hydrograph. So this can be developed in a spreadsheet in literally less than an hour. You can have everything you need to do this routing by hand. Now, that probably seems like a lot because when you use the software, you can do it in 10, 15 minutes. But what I was really trying to show you here is that the calculations are not that difficult. They're really fairly simple. And like I said, you can do it in a spreadsheet without too much difficulty. The last thing that I want to talk about is if you are interested in hydraulic design, and I'm not getting a kickback from this at all. I just think that this particular book is one of the best books that I've ever seen on hydraulics and hydrology and storm pond routing. And it's by a guy named John Gribbins, and it's called Introduction to Highway Hydraulics with Applications for Stormwater Management. And if you are going to get involved in this area or you're interested in this area, I would strongly recommend that you pick up this book. It's not that expensive. I think it's only like a $60 book. It's a soft cover book, so it's really not that bad. So that's really, that leads me to last, which is what questions do we have? We're a little bit ahead of time, but I'll try and answer any questions that I can from you.
Yes, so if you have questions, please type them into the questions area. I'll be reviewing those and getting those to Kevin or myself to answer. So let me get my camera on. So you talked a little bit about climate change, Kevin. What are you seeing as the impact climate change is having on how large storms are determined and the frequency determination? What impact is it having on the stormwater management and how calculations should be taking place?
So far, it hasn't, and most agencies are considering it more as extreme events than they are an actual change in the, so most agencies will create IDF curves and they'll create precipitation numbers for different events, and it hasn't been a long enough period of record to drastically change what the end result is. from a statistical standpoint. So generally, when you see people talking about what's the impact of climate change, they're looking at it more from an extreme event situation than just, let's say, if we did a design for a 10-year storm. A 10-year storm, even considering the last 20 years of record, isn't that much different than what the 10-year storm was before we had those 20 years of record.
So what has it done for those extreme events then?
Oh, it's huge. You can see it every day. I mean, hurricanes are more frequent. From anecdotal evidence, when we talk to different people in the industry, Texas is getting 10-year storms almost every year. And real extreme events, I don't know that we've had enough period of record to know that we're getting 100-year storms more frequently, but we are definitely getting those 10-year, 25-year, 50-year storms more frequently. And so are people designing for it yet? I don't think so. I don't think there's been a push yet to start designing for those larger frequency events.
Okay. I had a question about my statement of 28% void capacity in the backfill material and what that backfill material was. Typically, AASHTO 57 stone is typically like a 3/4 material, clean. It has a void ratio of approximately 40%. And so I think that's maybe the number that a lot of people are more familiar with. But the resulting porosity of it is 28%, and that means that 28% of the total backfill volume can be utilized for storage. And so that's what we're using. I don't know if you feel like 28%, 40%. I mean, it's your number to use. I think it's always better to provide a little bit of conservatism. So as 28% is our recommendation as published in our handbook. You may hear other engineers, other specific individuals recommend 40, but that's our industry recommendation for 28. I don't know if you have any thoughts on that, Kevin.
I have no reason to discredit you.
You know, I'm not going to discredit me. I'm just sitting here in my office. All right. All right. Let's move to. And please, if you have other questions, you can type them in. But we had a question back on figuring these storm frequencies. I think that's kind of the place where everybody starts this process, and it's one of those things. If you don't feel like you're starting in the right place, then how do you trust where you're ending up? But we talked about 10-year events. What about a situation where you're being asked to do a 10% storm exceedance storm for determining intensity? What do you think about that method of going about, I guess, determine your design storm, a 10% exceedance storm rather than a probability event?
Well, that's actually a 10% exceedance is exactly equivalent to what we would call a 10-year storm. Those are synonymous with each other. That's just, when you talk about a 10-year storm, you're just saying it's going to happen 1 in every 10 years. So 1 over 10, 0.1, that's your probability. So you have a 10% exceedance probability, which means that in any given year, you have a 10% chance that storm is going to occur. Something greater than that storm.
Okay. Very good. Yeah, there's all kinds of, obviously there's different ways that people talk about these things, but it seems to always come back to the same way of looking at it. So thanks for that clarification. You mentioned velocity a little earlier when you were talking about critical flows and things, but from a velocity calculation, a lot of time we're talking about volumes in stormwater flow, but velocity can be important both from the low end and from the high end. Do you have any guidance on that?
Generally, on the low end, you see recommended values between 2 and 3 feet per second for the design year, and that's fairly typical. I mean, depending on what agency you go to. On the high end, my personal opinion, 15, 16 feet per second. If you get much higher than that, you start getting really, really high square values, which can lead to some dramatic head loss that you really don't want, especially if you have junctions in the system. So in my mind, for a standard storm sewer, probably no more than 15 or 16 feet per second.
Yeah, and I think as an industry, we'd agree with both ends of what you talked about as far as a minimum velocity. And that's why I said, you know, on those detention systems, you're not going to get 2 to 3 feet per second making its way through those. And so if you're not collecting that sediment, it is going to settle out across the network, which is the last thing you want to happen. But 2 to 3 feet per second is commonly a clean out velocity, so to speak. And so that's kind of a minimum. And on the high end, yeah, we would agree with you. Anything approaching 15 feet per second presents a challenge, not just, I mean, you're talking about the hydraulic impact, but it also presents new challenges on the material itself. And as you have joints, and if those joints aren't perfectly aligned, every one of those is now being subject to incredible forces generated by that kind of water moving through it. And so, yeah, we would, if you have anything exceeding that kind of velocity, then you need to look at ways of reducing it. Now that can be done by stepping it down the grade, so to speak, and actually dropping it at structures so that you take some of that energy out of it inside a structure. Or you can look at other ways to do it. Like I said, you know, having dissipators or other types of ways. You know, we can, with a corrugated pipe, and you can have a higher Mannings, and that can slow it down some. But even there are times in steep slopes, I know we get calls from people doing designs in California or in the Rockies or something, and they're trying to bring it down a steep slope. And there's just so much you can do before you're not going to be able to control it, and you are going to exceed that. And so it is a real concern if you're trying to bring water down steep slopes.
Agreed. There's one question here about, I'm reading it, and it says, what for systems retention, what method do you use frequently? It depends on the owner. So if you're talking about a public agency, public agencies want nothing to do with, sorry, Dan, but they want nothing to do with underground retention, detention systems. They don't want them because of the maintenance involved with them.
Right.
If you're a developer, they love them because it maximizes surface footprint, and they're willing to absorb whatever maintenance is necessary for that particular system. So most of my work is in the highway industry for public agencies. So most of the time when I'm doing these, I'm working in either wet ponds or dry ponds. Those are by far the two most frequent that we use. But the calculation is identical. That's the interesting thing about these systems. No matter what system you use, calculations don't change.
Right. Very true. Yeah. And we, you know, can think of surface ponds. You can have underground ponds. It's you can have cement ponds, like Ellie Mae Clampett used to talk about. That's dating myself. That's like somebody who does hand calculations, or Kevin. So exactly. Anyway, all right. Well, I think we're going to wrap up. I know we're approaching our time, and thank you, Kevin, so much for presenting. It's great to have the primary author of chapters 5 and 6 to also present for us today. Hope you benefited from that, everyone attending. Just a couple of reminders. There have been questions about availability of the presentation. We have been recording this, and we will post it to our PPI website. If you go to the PPI, well, it's plasticpipe.org/drainage. Then go to the education pages. There's a webinar site where you can access these GoToWebinar recorded presentations. So that would be the best access to it. Following today's presentation, you will receive a survey. There's just 3 quick questions, multiple choice, so that we can get feedback from those who attended on this. So please take a moment to respond to the survey. And also you will GoToWebinar will generate a certificate of attendance. So if you're required to keep professional development hours, then that certificate of attendance should serve as your reminder of your participation in this today for an hour and a half. So again, thank you, Kevin. Thank you all for attending. and enjoy your day.
Thanks, Dan. Appreciate it.
Take care.